Thank you, Christina. Good afternoon. So this lecture will be about neutrinos and physics beyond the standard model. Of course, the topic is very large, so I will essentially focus on the new physics that is associated with the neutrino mass. So other aspects will be covered by Gabriela. So this is the plan of my lecture. Since I will start from the origin of neutrino masses, I will start by discussing Dirac versus Majorana neutrinos. Then I will argue that, as everybody I guess is already convinced that neutrino masses are an evidence for physics beyond the standard model. And I will spend some time talking about various models of neutrino mass generation. So this is the plan of the two lectures, not of today. I will then move on to discuss light sterile neutrinos, so the issue of anomalies, experimental anomalies that may suggest the existence of light sterile neutrinos has been already covered by Gabriela. So I will essentially present the theoretical framework and try to be complementary and not repeat things that she already said. Then I will discuss about possible manifestations at low energy of the neutrino mass generation mechanism, and in particular discuss about heavy neutral leptons and their experimental signatures. And finally, if time permits, I will discuss leptogenesis, and in particular low-scale leptogenesis that might involve some of these heavy neutral leptons. And this is what I intend to do today. I don't know if I will have time to finish this. So let me start by a general introduction, which will also repeat part of the things that have already been said. So there's been a considerable progress in neutrino physics over the past 25 years. And we have now, from oscillations in various sectors, evidence that neutrinos have mass and that they mix. And in addition to that, we have a more and more precise measurement of neutrino oscillation parameters. So I said before, there are 3 groups who are doing fits of neutrino data. So this is taken from this group, from new fits. So you can see the precision. So those error bars here are 1%. And overall, the 3 sigma uncertainties are between 3 and 8%, except for theta 2-3, for which they are larger. Another striking fact is the fact that, contrary to what we have seen in the quark sector, the mixed angles are large, with theta 1-3 being a bit smaller. In spite of all we have learned, there are still many open questions. So is CP violated in the lepton sector? So this will be discussed by Gabriel. I will not touch this. But in other words, do neutrino and antineutrinos oscillate with the same probabilities? There are already hints from the T2K experiment, which exclude at the 90% confidence level CP conservation in the lepton sector. There's been also a global fit from the NOVA and T2K experiment, but that does not bring much more insight into the question. Another question is, what are the absolute neutrino mass scale and the mass ordering? So basically the question, yes, the question is whether the ordering of neutrino masses is normal with delta m square 3 positive, or inverted with delta m square 3 negative. So we know already from oscillations that the heaviest neutrino should have a mass above 0.05 eV. So we have an upper limit on this effective neutrino mass parameter in beta decay from the Catherine experiment, which actually has been updated recently, which was presented at Neutrino 2024. I just learned this at lunch, which is now 0.48 eV. And finally, cosmology can also set a bound on the sum of neutrino masses, where the band that is quoted here depends, like all these bands, on the data that you use to produce the bands, and maybe should be taken with a grain of salt. And finally, the question with which I'm going to be, that I will discuss more specifically, the question of the neutrino nature. Are neutrinos Dirac or Majorana fermions? And a question that, of course, one cannot simply answer. One can just list possibilities. What is the origin of neutrino masses? So the standard model doesn't tell us anything about that, since at least in its original formulation, it predicts that neutrinos are massless. And this question of the origin of neutrino masses is actually closely related to the question of their nature. So let me first discuss the question of Dirac and Majorana neutrinos, which I will discuss quite in depth, maybe at the level that is maybe a bit too detailed for some of you, for those who are the most familiar with the question. So as everybody knows, neutrinos are the only fermions in the standard model that do not carry electric charge. So in principle, there can be their own antiparticles. And what do we know experimentally? We have observed only the left-handed neutrino and its CP conjugate, the right-handed antineutrino. At present, we cannot, I remember what I wanted to. Given the fact that all neutrinos we deal with are ultra-relativistic, we can identify helicity with chirality in all the discussion. So we don't know so far if the neutrino also has a right-handed component. If this were the case, then it will be an exact standard model gauge singlet. Hence, one could not produce it and observe it, okay? Just because it's a right-handed fermion, so it doesn't couple to the W, and in addition, it has no electric charge, so it doesn't couple to the Z boson. Now, the neutrinos that we have observed, so the left-handed neutrino and the right-handed antineutrino, can be equally well be described by a Dirac neutrino or a Majorana neutrino. The only difference is that the right-handed component of a Dirac neutrino is independent of its left-handed component, and we know that, as I said before, it is a standard model singlet, so we cannot observe it. While in the case of a Majorana neutrino, if you take the right-handed component of the Majorana neutrino, it is not independent of the left-handed component. It is actually its CP conjugate. So let me now describe in more detail how we can write a Dirac or a Majorana mass term. So suppose we want just to give a mass to neutrinos, so we add the right-handed neutrino to the standard model. And in that case, we can write a Dirac mass term exactly as we do for the quarks and the charged leptons. And here we have defined the Dirac neutrino as the sum of new left and new right. So it has two independent chiralities. We can represent its mass by this diagram here, which represents the transition between the right-handed neutrino and the left-handed neutrino. So obviously, this mass term preserves lepton number. There is an incoming neutrino and outgoing neutrino. But it violates the third component of weak isospin by 1/2 because nu A is a gauge singlet. This is not different from the other fermions of the standard model. So exactly like for quarks and charged leptons, this mass term is not invariant under the electric symmetry, but we can generate it from spontaneous symmetry breaking by a Yukawa coupling to the standard model X doublet, where H here is the standard model X doublet, L is the lepton doublet, and upon electroweak symmetry breaking, the X field acquires a VEV, V, and the Dirac mass is just given by a Yukawa coupling times the X VEV. So now the typical mass of the standard neutrinos implies that this Yukawa coupling should be extremely small, of the order of 10 to the minus 12, which might be seen as a problem. It's much smaller than the Yukawa couplings of the other fermions, even though the Yukawa coupling of the electron is 10 to the minus 6. So here I should add a little caveat, which I'm going to go back later. So we have added the right-handed neutrino standard model and written Dirac mass term, but in principle, it is also possible to add Majorana mass term for the right-handed neutrino, and in that case, it will turn out that we will end up with two Majorana neutrinos rather than a Dirac neutrino. I'm going to come back to this later. Let us now move on to the case of the Majorana master. So first, let me remind you that the charge conjugate of the Dirac spin-up psi of x, for instance, the one that described the electron, is defined as with the notation psi c, C psi bar transform, where C is the charge conjugation matrix that plays gamma matrix to its transpose. And for instance, if psi satisfies the Dirac equation with negative electric charge corresponding to the electron, then psi c will correspond to the positron. Now, with this charge conjugation matrix, we can form a right-handed spinor from a left-handed spinor. So if we now just take just the new left of the standard model, we define new RC. So R is here to remind us that this guy is right-handed, as C, new bar left transpose. So it's the same transformation as this, but it should be rather thought of as a CP conjugate, because charge conjugation is not just exchanges the particle with its antiparticle. It's not a spacetime symmetry. It cannot change chirality, so in addition to do that. So what this very simple argument shows is that the existence of a left-handed neutrino implies the existence of a right-handed antineutrino. Now that we have both left-handed neutrino and the right-handed one, we can write a Majorana mass term, which is just again a transition between left-handed and the right-handed fermion, but this time nu R is replaced by nu RC. And we can write this Majorana mass term here in the following form, where nu M is just the sum of nu L plus nu RC. The factor 1/2 here is just to avoid redundancy to count twice the same degrees of freedom. So this massive neutrino satisfies the Majorana condition, nu M equal nu MC, where again nu MC refers to this transformation, and it is called the Majorana fermion. So we can, in the same way as for a Dirac mass term, we can represent it by this diagram, or equivalently by a diagram in which two left-handed neutrinos exit of the same vertex. So this shows immediately that this mass term violates lepton number by 2 units, and also since nu L is part of an SU2 doublet, it violates weak isospin by 1 this time. So the conclusion is that a Majorana mass term violates lepton number. This is the signature of a Majorana neutrino. And because it violates weak isospin by 1, it cannot be generated by a coupling to the standard model X doublet, contrary to Dirac neutrino or other fermions. So Majorana neutrino masses require an extension of the standard model. So, okay. So different maybe way of saying the same things. We can think of a Dirac neutrino as describing 4 degrees of freedom. So I can think in terms of neutrino with spin up, spin down, antineutrino spin up, spin down, or it will be more convenient to think in terms of chiralities. So I have the right and left chiralities of the neutrino, and the same for the antineutrino. And it is described by a 4-component spinor, which I write in this form. I keep here a D to avoid, which I will drop immediately after, to avoid confusions here. The key point is that, as I said before, the left-handed and right-handed component of the Dirac neutrinos are independent. So now the Majorana neutrino satisfies this condition, the Majorana condition, and it describes only 2 degrees of freedom, can be viewed as being nu L and nu R bar. So again, I can write it as a 4-component spinor with a left-handed component and a right-handed component, but I'm just here writing in equations what I've said in words previously. But the left-handed components are not independent. If I take the Majorana condition and I act on it with the projector on the right chiralities, I will get that nu M right, which appears here, is nu MC right, And nu and C right, by definition, is just C nu bar M left transpose. Okay, so this just shows in equation what I was saying previously. So an important thing to notice is that the Maillard condition is consistent with any conserved additional quantum numbers. Suppose, for instance, psi carries a charge q. Then one can rephase psi by e to the I theta q. And under this transformation, psi c is going to change with the opposite phase. So obviously, this Majorana condition is no longer satisfied, is modified at least by this transformation. So this confirms the fact that only neutrinos can be Majorana fermions since they don't carry any conserved charge. And the same argument here implies that one cannot rephase a Majorana neutrino. And this is the reason why, in addition to the delta phase of the PMS matrix, the one that is analogous, sorry? Mm-hmm. The state will not be neutron and neutron, but the corresponding Majorana, say, eigenstates, like for Keron oscillation. Okay, okay. Okay, thanks. Yes, indeed, I was only talking about fundamental particles. Yes. So here I was just wanted to say that the reason why in the Majorana case the PNS matrix has two additional phases with respect to the Dirac case, which are called typically, I mean, just to distinguish them, Majorana phases, is precisely due to the fact that one cannot rephase the Majorana fermion. Okay, so if you remember the standard argument that you have probably seen in the case of the CKM matrix, so the PMS matrix is a priori unitary 3x3 matrix, which has in principle 6 phases, but not all these phases are physical. And by rephasing, so in the case of the CKM matrix, it will be, or let's take the PMS matrix. Suppose you are Dirac rephasing the charge lepton and the neutrino field. You can remove 5 relative phases, and you are left only with one physical one, which is the delta PMNS phase. Now, in the case of Majorana neutrinos, you cannot rephase the Majorana fields, or you will just remove, you cannot rephase them in the sense that you will just move the phase around. So it will appear elsewhere in the Lagrangian. So it's physical, it's not something that you can remove. So as a result, out of the 6 phases, you can only remove 3 of them by rephasing charge leptons. Okay, so this was probably very basic for most of you, but since the audience is diverse, I wanted to discuss this in detail. So how to distinguish Majorana from Dirac neutrinos? Again, this is going to be probably extremely simple for most of you, but sometimes I am surprised to have questions from people, including experimentalists, for instance, who are surprised, ask me, why do we say that ECP is violating the lepton sector, neutrinos and antineutrinos will oscillate with different probabilities? How can that make sense if neutrinos are Majorana fermions? So the answer is that the weak interactions are chiral, so they always involve not the Dirac or Majorana fermion, but it's chiral projections, so nu left or the CP conjugate nu bar R. As I said previously, and as I think it was very clear from the previous slide, they can be described by a Dirac or Majorana neutrino, okay? And so, and maybe what the common terminology, which maybe confuses some people when they think that neutrinos can be Majorana fermions, is that one calls the nu L the one that via charge weak interactions creates a negatively charged lepton. One calls him neutrino, and the nu bar right, the one that via charge weak interactions produces a positively charged lepton. One calls it antineutrino. So, And this is just due to the fact that, as Gabriela said in her lecture, one can define a U1 charge, which is nothing but the lepton number, which is preserved by all standard model interactions. And to do that, one assigns the same lepton number to, let's say, an electron and the left-handed neutrino, because the left-handed neutrino produces an electron, so +1, and the same lepton number, -1, to the positron and the anti-neutrino that produces a positron via charge current interaction. And exactly for the same reason, the same arguments, oscillation probabilities are the same for Dirac and Majorana neutrinos, because the production and detection processes are weak interaction processes. Okay, so, and then the only practical difference between the Majorana and the Dirac neutrino is the mass term, which violates lepton number by 2 units in the Majorana case. And to establish the Majorana nature of neutrinos, one needs to observe lepton number violation. So I will not discuss neutrinoless double beta decay, because this is going to be covered by Gabrielle in her lecture. So neutrino masses as evidence for physics beyond the standard model. So again, I guess that everyone in this room is already convinced, but let me review very quickly the argument. So neutrinos are massless in the standard model as it was defined historically. So let me remind you that there was in 1957, I think, an experiment called the Goldhaber experiment that measured the helicity and the neutrino and found it to be left-handed. So people just, when they constructed the standard model, they just added the left-handed neutrino without its right-handed counterpart. And that was perfectly in agreement with observation. And at that time, there was no hint of a possible neutrino mass, so that was everything was perfectly consistent. As argued before, with just nu L in the standard model, we can neither write a Dirac mass term nor a Majorana mass term. In the case of the Majorana mass term, it is because we cannot generate this mass from electroweak symmetry breaking if we only write renormalizable terms in the standard Lagrangian as one should do, except nowadays where we expect some new physics beyond the standard model required by neutrino masses, dark matter, etc. And in the absence of, if we don't want to pick up a precise sphere, a precise model, we work in what is called SMEF, standard model effective theory. We add up to the standard Lagrangian non-normalizable operators. Okay, so now do we need to go beyond the standard model? Then it becomes maybe a question of terminology. If we add the right-hand neutrino to the standard model, it looks like a very simple modification. We just add the right-hand neutrino to be able to write a Dirac mass term, but then I'm going to make this argument more precise. If you add the right-hand neutrino to the standard model, you can write a Majorana mass term for the right-hand neutrino, and you end up with a Majorana mass term. And to be more specific, the moment you add the right-hand neutrino to the standard model, lepton number violation becomes a possibility. So because this Majorana mass term violates lepton number, and this introduces a new mass scale, the scale at which lepton number is violated. So it really means, in my opinion, physics beyond the standard model. So let me now make things a bit more explicit, and let's add the right-hand neutrino to the standard model. So to avoid thinking of it as the right-handed component of a Dirac neutrino, let me denote it by NR with a big N here. So we have, of course, the Dirac mass term already discussed. And in addition, we can add in the Lagrangian a Majorana mass term for the right-hand neutrino, which can be, we can write in this way, nu LC bar nu R, or with the charge conjugation matrix appearing here explicitly, nu r transpose C nu r. So this mass term, as we have already seen, violates lepton number, but at variance with the Majorana mass term for the left-handed neutrino, which violates SU2, this one is perfectly allowed by electroweak symmetry, since NR is a gauge singlet. It's an electroweak singlet. So there is no, and it's of course also allowed by Lorentz invariance. So it's a term that is allowed all fundamental symmetries of the sound model. So we must write it unless we impose lepton number, which again would be is in principle something we are not allowed to do. So in the standard model without right neutrino, the statement is that lepton number is like baryon number is a global symmetry of the theory, but it is just what is called an accidental global symmetry. It's just that with the field content of the standard model, gauge invariance, Lorentz invariance, and renormalizability, there is no way to write a term in the Lagrangian that violates baryon or lepton number. So in other words, those global symmetries are not fundamental symmetries that do not have the same status as gauge symmetries. They are just accidental symmetries when they are there. Okay, so let's do that. We have this Dirac mass term and this Majorana mass term. And to find out what the mass against it are, we need to diagonalize this mass term, and the simplest way is to put them in a matrix form. So I put nu L and nu LC, the CP conjugate of nu R, in a vector. So the mass matrix is then written in this way. We here the Dirac mass and here the Majorana mass. I forgot to say that obviously I work in the one family case. That's why this is a 2x2 mass matrix. I can diagonalize it with an angle theta, and this gives me a diagonal matrix with two eigenvalues m1 and m2, and the eigenvectors are nu L1 and nu L2, which are combination of nu L and NLC. So now I can define nu m, nu mi as the sum of nu li plus nu ri c, such that the Majorana condition is satisfied by this state. And the conclusion is that we end up with two Majorana neutrinos with masses m1 and m2. So this conclusion is completely general. So if you add the right neutrinos to the standard model, you end up with Majorana neutrinos. Now there is a limit that is very interesting, which is known as the CISO limit, which consists in assuming that M, the Majorana mass, is much larger than the Dirac mass. Why is this something natural? It's natural because the Majorana mass, remember, is generated by electroweak symmetry breaking, so it is naturally smaller than the electroweak scale, while the Majorana mass is unconstrained by the electroweak symmetry. So it can be, we can take it as large as we want. So let's consider this limit. And then we can express M1 and M2 as well as the mixing angle theta in terms of MD and M with this simple formula. So M1 is MD squared over M. And due to our assumption, this is much more than the electroweak scale. Even if MD is of the order of the weak scale. M2 is approximately equal to M, the Majorana mass, and is much larger than the electroweak scale. And finally, the mixing angle is equal to MD over M, and is again a small number. So if we go back to these equations, we see that basically sine theta is very small. So what we conclude is that the lightest mass eigenstate is essentially the standard model neutrino, the left-handed one, while the heavier one is essentially the original right-handed neutrino. So the conclusion is that we have a natural suppression of the mass of the standard model neutrino given by this formula here, while the other one remains extremely heavy. This limit, we can also view it the following way. I talked about the sound model as an effective field theory previously. So if we work in the theory at a scale much lower than the Majorana mass, we can integrate out the right-hand neutrino and write in the standard model Lagrangian or in the Smash Lagrangian all non-renormalizable operators that are generated by this right-hand neutrino. And this includes this famous dimension for 5 operator, which is just LH squared and is known as the Weinberg operator. So you see immediately that if when the Higgs field acquires its value, this will generate a Majorana mass term for the standard model neutrino. So there is a very immediate new physics interpretation of all this. We can identify the Majorana mass M with the scale of new physics responsible for lepton number violation. There is no a priori prediction for this scale. It could be very low, it could be around, so here I assume a specific limit which has the advantage of explaining the smallness of standard model neutrino masses, but in principle, I could take it as low as the Wick scale, or even in so-called low scale seesaw mechanism, or even below. I would lose the advantage of explaining the smallness of neutrino masses, but in principle, this is a valid possibility. Or I could take it very large, up to, let's say, 10 to the 15 GeV. And the reason why I stop here is that if you take a larger Majorana mass, you would end up with a light neutrino mass smaller than the one suggested by the atmospheric neutrino oscillations, unless the Yucca coupling is in the non-perturbative regime. Okay, so this was the one family case. So all these generalizes very easily to the free generation case with 3 right-hand neutrinos with Majorana mass M. Majorana mass is Mi. So here I work in the mass eigenset basis of these heavy neutrinos. Now this is the Dirac-Yucca coupling with the Yucca couplings Y I alpha, which are now 3x3 matrices. So I goes from 1 to 3 for the 3 heavy for the 3 right-hand neutrinos, and alpha for the 3 flavor standard model neutrino, flavor eigenstate. And I get this formula for the light neutrino mass matrix, the one that describes the mass and mixing angles of the standard model neutrinos. Y transpose m minus 1 y multiplied by the square of the X valve. And I can diagonalize it by a unitary matrix U, which if I work in the charge lepton mass eigenset basis, which I assume implicitly here by giving these labels to the lepton doublets, then U is nothing but the PMNS matrix, and D is of course diagonal matrix with whose entries are the light neutrino masses. Sorry. Okay, so this was the general discussion. Let me now try to embed this mechanism in more fundamental extensions of the sound model. So one of the reasons why the seesaw mechanism is considered to be very attractive, I've seen already that it explains the smallness of neutrino masses, is that it is naturally realized in grand unified theories based on the SO10 gauge group or larger for 2 reasons. The first one is that in SO10, all standard model quarks and leptons fit in a single representation, which is the 16-dimensional spinorial representation of SO10. And if you count carefully, taking into account quark flavor, you will find out that there are only 15 fermions per generation in the sound model. So there is one additional state and this state has precisely the quantum number to be a right-hand neutrino, in particular just because it is a standard model singlet. The second interesting aspect of SO10, we have seen previously that in the general seesaw mechanism, the Majorana mass M was an arbitrary scale, which was not constrained by any spontaneous symmetry breaking. In SO10, it is different because in SO10, the right-hand neutrino is no longer a gauge singlet. It carries quantum numbers under SO10, and its mass, in fact, is related to the symmetry breaking of SO10. You want to break SO10 down to the standard model gauge group SU3 cross SU2 cross U1, and typically the right-hand neutrino masses will be generated when you break cell of SO10. So the masses of the right-hand neutrino scale will be naturally associative with the breaking of the baryon minus lepton number. So it's no longer an arbitrary scale, even though, of course, it is model dependent. Depending on the SO10 model that you consider, these masses will have different values, and that they depend also on couplings in your Lagrangian. So as said before, if you want to have natural values of the Dirac-Yukac coupling, let's say you want them to be of order 1, this suggests a Majorana mass of the order 10 to the 15 GeV, which is near the scale at which gauge couplings unify, at least in supersymmetric extensions of the standard model. So this is as a function of the energy scale, as the evolution of the gauge coupling. More precise, alpha I minus 1, where alpha I is gi squared over 4 pi. And in dashed line, you have the evolution of these gauge couplings. In the case of the standard model, you see that they do not really unify, they do not cross at a single point, while if you include supersymmetry, depending on the mass scale of the superpartners, you can find reasonable unification of the gauge couplings. So that's an example of realization of the seesaw mechanism in a specific theory extension of the standard model. There is another one that I would like to discuss briefly, which is the one in which actually the seesaw mechanism was first proposed by Minkowski in so-called left-right symmetric theories. So left-right symmetric theories were proposed in the 17th. So this was an attempt to restore parity invariance, which is broken by electroic interactions in the standard model. So people proposed to extend the standard model electroic gauge group SU2, where is it, sorry, SU2 left cross U1y to SU2 left cross SU2 right cross U1b minus well, where this U1 is associated with the baryon minus lepton number. This SU2r is the analog of SU2 left, the same way as SU2 left acts on left-handed doublets of fermions. SU2 right acts on right-handed doublets, not just fermions, by the way, also SU2 left also acts on the X doublet. So in those theories, you also have a B doublet, which has also transformed under SU2 right, but focusing more specifically on fermions. So SU2R will act on quark, right-handed quark doublets, and left-handed lepton doublets, meaning that these theories automatically predict the existence of a right-handed neutrino. So by construction, you need a right-handed neutrino. The reason also why these right-handed neutrinos must imperatively be present is that you want to gauge the B minus cell quantum number, and in order to gauge it, you must make sure that it is anomaly free, and with the standard model field content, fermion content, it's not the case. So you need to add one right neutrino per generation to have B minus L anomaly free and be able to gauge it. So associated with this new gauge group, so the left-right symmetric models, I forgot to say that I'm presenting here a sort of minimal version. The model contains W right, which is the analog of W left for now for SU2 right, and the Z prime gauge bosons. And the right neutrino couples to the W right with the electron right, and it also couples to the Z prime gauge boson. So it's no longer a gauge singlet. Now, what we observe at low energy is not a left-right symmetry. Symmetry parity is maximally broken by weak interactions. So one should break spontaneously this gauge group down to SU2 left cross U1 Y. So this is done by this step in which SU2 right cross U1 B minus L breaks down to U1 Y. And then the hypercharge is given by this relation T3R plus B minus L over 2, where B minus L is just the baryon minus lepton quantum number, and T3 right is the third component of SU2R isospin. So how do you realize this left-right symmetry breaking? It can be realized by giving a wave to an SU2 right triplet delta R, which has charge components and the neutral component. So it's of course this component that gets a wave. In the process, WR and Z prime that we have not observed become very heavy, so they get a mass. And at the same time, this spontaneous breaking of the left-right symmetry generates a Majorana mass for the right neutrino. So indeed, you can write the following coupling between the SU2R triplet and two SU2R doublet, lepton doublet. So this is perfectly compatible with this gauge symmetry. So when the neutral component of delta R across the wave, you get here a Majorana mass term for the right neutrino, which is given just by here there is some coupling and the wave VR. As a consequence, the standard neutrinos become massive. They get a Majorana mass through the seesaw mechanism. Okay. So some general comment, which, as I said previously, right neutrino, in fact, this looks like a very simple minor modification of the standard model, but in fact, it's a deep modification of the standard model. As I said before, we thought right neutrinos the baryon and lepton would be accidental global symmetries of the standard model. This is no longer the case in the presence of right neutrino. So let me then summarize the arguments pro and against Dirac neutrinos. So why are Dirac neutrinos not very natural from a theoretical perspective? First, because you need to impose lepton number. Second, you need very small Yukawa couplings to explain the smallness of neutrino masses. Of course, you could always say that a theory flavor might explain that exactly like it explains the smallness of the electron Yukawa coupling. And why are Majorana neutrinos on a better footing from a theoretical perspective? Lepton number is violated in many extensions of the standard model. I discussed two. Because you need to break the left-right symmetry breaking. Sorry, you need to break the left-right symmetry. Because we don't observe it in nature. We observe that parity is violated by weak interactions, and you must break it obviously at a scale which is above the electroweak symmetry breaking to make those W right and Z prime very heavy. There are, by the way, I didn't speak of it, but there are searches at the LHC and the current bound are, I don't know exactly, in the several TeV range. Okay, so lepton number is validated in many extensions of the standard model. Any mechanism that generates neutrino masses without writing neutrinos give Majorana neutrinos. We have seen that this is natural in quantum unified theories and other theories like left-right symmetry, symmetric theories, or supersymmetry without R parity. So maybe now supersymmetry is less fashionable than it was in the past, but I just mentioned it for completeness. They provide a possible explanation of the smallness of neutrino masses. And another interesting aspect, which I will discuss at the end of the second lecture, is that Majorana neutrinos, especially in the seesaw mechanism, open the possibility to explain the antimatter asymmetry of the universe with exactly the same ingredients that explain neutrino masses in the seesaw mechanism. And of course, having said all that, we must of course wait for experiment to tell us what is the true nature of neutrinos. We cannot decide just on the basis of theoretical arguments. So let me now discuss alternative mechanisms of neutrino mass generation. All of them are without right-hand neutrinos. First of all, there are other versions of the seesaw mechanism. So the so-called type 2 seesaw mechanism and type 3 seesaw mechanisms. I'm going to describe them just after. And as I will mention also, one can realize them like the type 1 seesaw mechanism, either at low energy or at high energy. A completely different class of models are so-called radiative models, where neutrino masses are generated at some loop level, one loop, two loops, possibly higher. And the idea is that neutrino masses are small because you get a loop factor plus, it's not enough, of course. One loop, not even two loops, is not enough, plus some couplings that are also need also to be small. These models are typically low-scale models. Of course, there is some arbitrariness in the couplings, but typically they are low-scale models, so you have possibly the possibility to test them at colliders. And there are more exotic versions that I just mentioned in passing, like supersymmetric models with R parity violations. So if you don't know what R parity, it is what explains the stability of the lightest supersymmetric particle in supersymmetric models. So if it is violated in practice, you introduce lepton number violation and possibly also baryon number violation. And a completely different class of models are models with extra special dimensions, where I will not say much, except the simplest version are excluded by neutrino oscillation experiments, essentially because they would predict oscillation with a large mixing angle of the active neutrinos with an infinite tower of sterile neutrinos. Okay, so let me briefly review the type 2 seesaw mechanism. So in the type 2 seesaw mechanism, you like in the type 1, you also generate like actually in all models I'm going to discuss, you generate the Weinberg operator, but now the state that is exchanged is no longer a right-hand neutrino. It's an electroweak, a scalar electroweak triplet. And actually, it was first proposed as a low-scale mechanism, just by noting that the Majorana mass term for the left-hand neutrino violates the third component of weak isospin by 1. So in principle, as said before, you cannot generate it by a coupling to the X doublet of the standard model, but you can generate it from a coupling to a X triplet. The coupling L alpha L beta and this delta L, which again has a neutral component. You also need, in order to generate a wave, to couple this triplet to the, well, not just to generate a wave, but also to generate neutrino masses, because in the end, you should generate the Weinberg operator. So you should, this triplet should couple both to leptons and to the X doublet. So you need, in addition, a coupling like this one between the X doublet and the triplet in the scalar potential. So I wrote here that this mu parameter violates lepton number. In fact, you could, it's the simultaneous presence of both couplings that violates lepton number. You could always give a lepton number -2 to delta, such that this is invariant under lepton number, and then it is that coupling that violates lepton number. Or do the opposite, say that delta has no lepton number, so this preserve lepton number, but this violates lepton number. Whatever you do, you always need a breaking of lepton number, which is not surprising, since this operator, as we know, generate Majorana neutrino masses. And again, even though I say that this can be realized also as a low-scale mechanism, you can again take the CISO limit where the triplet, the X triplet, is very heavy. And the advantage is that, again, you have a natural explanation for the smallness of the standard model neutrino masses. They are suppressed by, as given by this formula, mu over n delta squared. And an interesting feature is that here you have these F alpha beta couplings that are Yukawa couplings that are, I call it Yukawa, the couplings to the couplings of the scalar triplet to the leptons that are symmetric. So the neutrino mass matrix is directly proportional to those couplings, so which makes it more economical in parameters than the type 1 CISO mechanism. A difference with the type 1 CISO mechanism is that the triplet mass is a priori not related to the lepton number violating scale. In fact, you could even have lepton number violation at a low scale by taking this parameter here, mu, to be very small. Okay, so just to say that you can also realize the type 2 CISO mechanisms, or mixed type 1 plus type 2 CISO mechanism in Grant unified extension of the standard model. Let me not insist on it. And move on to the, sorry? Yeah. More economical in parameters, meaning that you have exactly the same number of entries in the standard model neutrino mass matrix as well, at least the flavor couplings, because you have also mu and m delta here. While in the type 1 CISO mechanism, you have this Yukawa matrix Y, and which is not symmetric, and the free right-hand neutrino masses. So I didn't count completely the number of parameters, but yeah, yeah, exactly. I didn't do the precise counting, but this one is symmetric, like. Yeah. Yeah. Yes. This. Yeah. It's not the. I mean, one of the problems of Grant unified theories, which are a very compelling mechanism, simplicity of structure, but when it goes to constructing an explicit model that satisfies all phenomenological requirements, it becomes very much complicated. How much time do I have left? A few minutes, okay. So I guess I will not address sterile neutrinos this time. And okay, in a few minutes I can finish. So okay, let me just say about the type 3 CISO mechanism that it's very similar to the type 1 CISO mechanism in the sense that here um, you have a coupling of um, sorry, yeah, in terms of the structure of the coupling, sorry, you have in the type 2 CISO mechanism you can generate three light neutrino masses with a single heavy state. I forgot to say, I'm sorry, in the type 1, I guess most of you know it already, but that in the type 1 CISO mechanism, if you have just right neutrino, you give mass only to one light neutrino. If you have two right neutrino, you give mass only to two light neutrinos, and you need three right neutrinos to give mass to three light neutrinos. So in the type 1 CISO, the minimal number required to explain oscillation data is two right neutrinos, because we just need to explain 2 delta m squared. We don't know the absolute mass scale. This is the same story here in the case of the type 3 CISO mechanism. So the structure of the coupling is the same. Here it's a bit symbolic, but if you have three fermionic triplet, there will be an index I, like in the type 1 CISO mechanism. So you see also that the parametric dependence of the neutrino mass matrix is also the same. So I won't say much more about it. And again, you can accept that again you can try to realize this mechanism is in Grant unified theories, but I will not say much more about it. And also you can have a realization of this mechanism at low scale with the possibility to possibly produce these states at collider. And rather easily, because another thing I forgot to say is that a difference with the type 1 CISO mechanism. In the type 1 CISO mechanism, the right neutrinos are standard model gauge singlets, so producing them is not so easy. You must produce, even though they are in the GVTV range, you need to produce them through their mixing with the active neutrinos, while in the type 2 and the type 3 CISO mechanism, they are charged under SU2. So you can produce them by gauge interactions. So if they are at the right scale, producing them at colliders is not complicated, meaning that you can constrain them. Okay, so now radiative neutrino mass model. I think I just have two slides. So this is the prototype of the radiative neutrino mass model, the so-called Z model, which is a one-loop model. In the Z model, you add to the standard model a second X doublet that you call phi, and an SU2 singlet, H+, which has an electric charge. In this way, you are able to write the following terms. First of all, since you have a second X doublet, you can write UK couplings for the charge leptons depending on H and also depending on phi. So you have two possible contributions to charge lepton masses. One for the standard model X, H, and one for this new X doublet phi. Second, you can write a coupling between two lepton doublets and this new SU2 singlet H+. Since it is an SU2 singlet, you need to contract the SU2 indices of the lepton doublet in the singlet combination, meaning that these coupling F alpha beta are antisymmetric. So there is a smaller number of them. And finally, you can write in the scalar potential a coupling between H+, H, and phi. So this is the diagram that generates neutrino masses. So you see that here you have this coupling here to H+ that appears at this vertex. Here at this vertex, and here you have just the contribution of phi or H to the charge lepton masses. And finally, you have this coupling here that appears here. So the signature of this model are typically new exotic states that you can possibly produce at colliders if they have if they are kinematically accessible, and they can also contribute to rare processes such as flavor violating decays of charged leptons, like mu2e gamma. Usually we get the impression that in all these models, we have so many parameters that there's no possibility to exclude them just on the basis of neutrino oscillation data. In fact, the Z model, well, at least the original version of the Z model, where phi was not contributing to the charge lepton masses, was very predictive because these couplings were antisymmetric. And in fact, it was predicting a very rigid structure of the light neutrino mass matrix with an inverted mass ordering and a near maximal solar mixing angle, which we now know is excluded by data. So that's an example of a model that was excluded just on the basis of oscillation measurements. I'm cheating a little bit because it's, after all, you can say it's a parameter choice to say why these couplings to 0. Anyway, that was the original version. I said that I will not say much about supersymmetry with r-parity evaluation, but you can also have, in this case, one loop contribution to neutrino masses. And this is just an example of a two-loop radiative neutrino mass model, the Z-Babu model, where now you have two charged SU2 singlet scalars, H plus and K plus plus. H plus has the same coupling to lepton doublets as in the Z model, while K plus plus couples to right-handed charged leptons, and you get a neutrino mass matrix that is suppressed by all these couplings, and also you need some charged lepton mass insertions in these two loop diagrams, so they're also suppressed by charged lepton masses. So you can get small neutrino masses without requiring two small couplings. And I think that is, let me just check. Yes, the other one was sterile neutral, so I think I will stop here. Ah, okay, okay. Yeah, it's true that if you think of several observables, like you mentioned, proton decay, charge lepton flavor violation, you need basically to choose a specific extension of the sound model, and then it becomes model dependent. I think the sociological evolution that you are mentioning is that after having put so many ops in some specific theories like Grant unified theories, and we are hoping for super chemical to discover proton decay or supersymmetry, and we were hoping for LHC to observe superparticles. There has been a sort of people have thought, okay, we were not successful in picking the right theory, but we know that there must be some physics beyond the sound model because of neutrino masses, dark matter, the matter antimatter asymmetry of the universe. So let's do effective field theory, and let's try to see. Let's write the most general effective Lagrangian based on the standard model neutrino. Based on the standard model content, and see whether we can from one constraint, from one observable, we can constrain some coefficient in the some Wilson coefficient in the Smith Lagrangian, and then obtain some constraint on other observables. It's not always possible because there are many operators, a very large number of them, but in some cases you can say something. So it's a different way of trying to explore new physics.
Usually stand for nucleon decay experiment. Now they change for neutrino detector. Very smart move, but indeed they still insisting on this scientific goal of searching for matter stability. Yeah. Absolutely. They were looking for proton decay, and neutrinos were the problem they have with material. They now face the failure because they haven't seen proton decay. They switch, but the original experiment was searching for proton decay. I mean, they achieved the gold mine, and they take fantastic use of them. But I mean, this means that you need to look for where you look and find this proton decay. No, because they have done an excellent use of not finding proton decay. But the thing was, well, we didn't even care of the theory in the beginning. Someone told you they were not able to distinguish electron from neutrino. So they were background to get rid of. And then we can do that, make this topological distinction between muon rings and electron rings, and just change the whole hierarchy of physics.
Yes. Sorry? Yeah. Yeah. No, the fact that they're charged implies, yeah, some constraint. Yeah, there's certainly some constraint. Yes. Yeah. 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 Yeah.
These particles, for instance, this K plus, yeah, but these are heavy and are stable. Yeah.
You are talking of mu gamma,
No, 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 no. The fact that they are electrically charged, so it's very easy to produce them and to put constraint on them. This is true, but it's. I mean, we. Yeah, yeah. Of course. I mean, you can always increase the mass.
They are heavy.
Yeah.
So maybe the accelerator is not sufficient to
Yeah.
generate.
It's the same kind of hope that we have. I said previously that these electroic triplets, in principle, that they can be very efficiently produced by gauge interactions. So for the time being, we just have lower bonds on them, and maybe someday we will get discovery. I mean, I wouldn't bet on it in the sense that those models were constructed to solve a problem, to explain neutrino masses. So it's difficult to say if a model is likely to be realized in nature. If I would have to bet on something, I would probably bet for the simplest possibility, which is the type 1 seesaw mechanism. I guess like probably many people.
This paper of Minkowski that you mentioned several times, it's just retain the neutrino, nothing else.
Yeah. In left-right symmetric theories, no?
Pretty sure. Let's check.
Okay, let's check, because I thought it was in the context of left-right symmetric theories.
So, Minkowski and Fitch produce the SO10 model together with Giorgiai.
Mm-hmm.
But then the conclusion that neutrino are massive is subsequent. So first there was the paper of Fitch and Minkowski and Giorgiai on SO10. They produced the general framework, but the deduction that neutrino have Majorana nature and this is so apply is later, and only Minkowski with just sterile. And this paper, in fact, assumes that retain the neutrino is 50 GeV in order to have mu e gamma. The title of paper is mu e gamma
At a rate of 10 to the minus, yeah.
It's just a phenomenological paper to say if retain the neutrino are so light, maybe we will check it.
Yeah.
In a sense, it does not believe in seesaw. It says if you're just seesaw, I mean, it's not much. It's not physical.
Yeah, because at that time, I think, there was no particular reason to suspect that neutrinos were massive.
Yeah, people do not believe much in,
Yeah.
in massive neutrino.
Yeah.
What was the motivation for left-right symmetric models at that time that people asked? Because now
It was, as far as I know, because it was in the 70s, the motivation was doing theoretical to restore evaluations where nowadays we're used to it, so we don't complain, but they were a bit disturbed by the fact that weak interactions violate maximally parity. So somehow they thought, I don't know why, that parity should be a symmetry of nature, or maybe this was, I don't know. They were trying to think of some extensions of the weak interactions as we knew them, and they came up with this idea. And it was also to some extent the first step towards unification, or maybe in parallel, because I presented the minimal left-right symmetric model, but you have also the Paty-Salam model, which is SU for C cross SU to left cross SU to right, where basically the fourth color corresponds to leptons. And it turns out that these left-right symmetric group, they are intermediate step, depending, there are different ways to break SO10 because it's a large group into the standard gauge group. There are different paths you can follow, and some of them have as intermediate gauge group left-right symmetric group. So there are many motivations for those models. Not even mentioning the fact that, a W right, for instance, or Z prime is something that is easy to look for at the LHC. Now, if those theories are really exist and the mass is 10 to the 5 GeV, the LHC has no chance. But machine that works, let's look for these objects. Thank you.